So it's been a while, but here is another video finally. So there are going to be a few notes to take today. Make sure you get these notes down because in class we will be discussing a lot of this stuff. But again, if you have the notes down, it's going to be much easier. And as always, if something doesn't make sense, please let me know so we can go over it more in class. If you would like to follow along in the book, this is actually going to be from two different chapters, a little bit from chapter 10 and a little bit from chapter 11. Okay, KMT. What is KMT? Well, you may remember from class that KMT stands for kinetic molecular theory. It's basically explaining to us that all molecules are constantly moving around, and when things collide, this is when reactions can take place, provided the energy is enough. Now, technically, if we're going with a very strict definition, kinetic molecular theory only applies to gases. So let's just take a look at what that means for us right quick. First of all, gases are made up of tiny particles, and for our purposes, we can assume that these gases do not take any volume up. Their particles don't take up any volume, so they're points. Gas particles collide elastically. And what does elastic mean in this sense, you may be wondering? Well, similar to an elastic rubber band. You pull it, it snaps back to its original shape. What it's saying here essentially is that we can assume that when gas particles bump into each other, if there's not a reaction happening anyway, that they bounce off of each other and continue on in a new direction, but with no loss of kinetic energy. That's what elastic means, that the collision had no loss of kinetic energy. 3. The gas particles move around continuously. They don't stop. 4. There are no forces of attraction between the gases. So it's not like there's any gravity or magnetism pulling them together. And 5. The temperature of the gas depends on the average kinetic energy of the particles, as we demonstrated in class last time. That's kinetic molecular theory as it applies to gases. Now, we can use this to understand a few things about how gases work. You may be wondering, why is a train here? Well, it's not just any train, but a steam engine. Steam engines, of course, steam is water vapor. That's going to be a gas. It's going to act as a gas. So first of all, gases can expand. They don't have a set volume. You'll remember this from all the states of matter stuff that you've been doing for years now. So gases can continue to expand and expand and expand. Gases are fluids, just like liquids, which means they don't have a definite shape. They can move and flow past each other because, from kinetic molecular theory, there's no forces of attraction between them. Gases have density, very, very low density. In fact, about 1,000 times less dense than liquids or solids, which is why gases, although they have mass, it's not that much for a given unit of volume. Compressibility, you can take a gas and you can squeeze it down. You can have compressed air. Compressed air is stored in these very, very well-built metal tanks, and if the nozzle on those break, they can actually do quite a bit of damage. It's just air, but it's under a lot of pressure, up to 100 times more pressure than air. That can be dangerous. Gases can diffuse. You know diffusion from biology. Basically, if you have a gas in one place, all those particles, since they're constantly moving around, are going to spread out and fill the whole space available. Okay, now, very important distinction here. Kinetic molecular theory technically only applies to gases, and technically as well only applies to what's called an ideal gas. Now, what gases are ideal gases? Well, let's think back. Let's actually go back a slide here. So, gas particles move around continuously. Well, that's going to fit just about everything. there are no forces of attraction between gases. Now, is that necessarily true? No, we've talked about different attractive forces, I believe, and if you'll think back to the different types of bonds that we did and intermolecular forces, you may remember we had dipole-dipole forces, and we had hydrogen bonding, and we had London dispersion forces. Everything's going to have London dispersion forces. Some will be greater than others. Let's look at number one. Gases are made up of tiny particles, and you'll recall it doesn't say it here, but I mentioned it, that kinetic molecular theory assumes that they take up no space. Well, we know that's not true. They're going to take up some space. So that means there is no such thing as an ideal gas. However, a lot of gases come close enough, we can assume that all of those 5 points are true. That's good enough for our calculations. Some gases are more ideal than others. What group of gases on the periodic table would be the most ideal, would you suspect? And if you said noble gases, you're right on, because remember, they're happy the way they are. They're not going to need to react with other stuff, so they will be, in most cases, the closest to an ideal gas. We need a couple of important definitions for matter, particularly gases, in order to do what we're going to do next class. Next class, we're going to work out all of the algebra that we're going to do this chapter from experimentation. This is the Vernier gas pressure sensor. We're going to use it with the LabQuest next time and figure out the relationship between different properties of gases, such as pressure. Now, I'll have a slide about pressure in just a minute, but real quick to start, pressure is basically force per area. Sometimes you measure it in PSI, which is pounds per square inch. Of course, we're not going to do that in science class because neither pounds nor inches are SI units. Volume. Well, you'll remember that volume is the amount of space that something takes up. If it's matter, it's got volume. What was a property that we talked about last class that could apply here? Has to do with the speed of the particles moving around. Temperature, right, temperature. So that's going to be related to the average kinetic energy of the gas, and also we'll need to take into account the amount of gas particles that we have. And what's the SI unit for amount? Dealt a lot with it last chapter, and it's the mole. The mole. We're going to measure amounts in moles. These four things are the only variables we're going to have in this whole chapter. Here's the last slide, and then we're done for today. I promised a little bit more information on pressure. Now, first of all, the unit for pressure, the SI unit for pressure, is the Pascal, abbreviated PA. It's technically 1 Newton distributed over an area of 1 square meter is the definition of 1 Pascal. Don't worry too much about that. That definition doesn't mean a whole lot, but I mean, if you have more pascals, that means you're going to have more pressure. Now, there may be other units that are more familiar to you for pressure. Go ahead and pause the video, take just a couple of minutes, maybe look at the book, maybe Google it, try to find some other units as well as their conversion from one to another. I'll, of course, give you the conversions on a test, but it might be helpful to have them in your notes. Go ahead and pause for a minute and do that. Okay. And you should have found such things as millimeters of mercury, or atmospheres, or PSI, or torr, things of that nature. Now, how do we measure pressure? Well, the traditional way of measuring pressure is with a device called a barometer. Here is a traditional barometer. We'll be using ones that actually don't use mercury like this one. Next time in class we'll be using electronic barometers. But essentially, this is an old style barometer used for measuring air pressure. What happens is you've got sort of an inverted test tube here. There's a container of mercury here, Air pushes down on the mercury, and depending on how much pressure the air is pushing with, the mercury has nowhere to go but up into the tube. Higher air pressure means it's going to go higher. Lower air pressure on the outside means that the mercury will drop. So this is why one of the traditional measurements of pressure is millimeters of mercury. Also, this is what it means if someone says the barometer is falling in terms of weather, it means the air pressure is dropping, which often means a change to more stormy weather, perhaps. Related to pressure is a term called STP, that is standard temperature and pressure. The pressure and temperature of chemical reactions can affect their outcome, so most times we try to perform scientific experiments as closely as we can to 1 atmosphere of pressure, so that's equal to the air pressure at sea level, and 0 degrees Celsius. That's going to be STP. We try to perform all experiments as close as we can to those conditions. I mean, the 0 degrees C is a little bit hard to do in our classroom, but if we ever do anything very specific, we'll have to take that into account. One quick more thing about pressure, and that's just Dalton's law of partial pressure. You've heard Dalton before. Do you remember what he gave us? That model of the atom, remember what it looked like? Just a little ball. So he also worked with gases, and he helped to show that if we're measuring the pressure of a gas, and there's a mixture of gases there, that very simply the total pressure is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on, continuing like that. That's Dalton's law of partial pressure. We'll do a calculation with that next time in class. Just get the equation down right now. It's pretty simple. Again, it's P1 plus P2 plus P3. That's it for today. Don't forget to do the whisk.